teaching Adam up since he's our one kiddo who's gone today. We were just talking about why you probably would have stopped or needed to have stopped around numbers 13, 14, which doesn't give you a lot or didn't give you a lot that you could have done unless you had gone looking at examples in the book. Because it's a component form. Haha. All right, let's talk about it. Component form. Remember how yesterday I drew that kind of complicated diagram of vectors that had like a ship going from some origin point out, and then it like did a little detour, and someone is sick and they're needing to be rushed to the hospital and their family is trying to meet them, something like that. Okay? And I was like, ugh, this could be a mess if we had to break this into oblique triangle to figure out with geometry what everything is. It would be a lot easier to break this down or to break these down and talk about the horizontal changes and then the horizontal changes. I should go here, I suppose. And then the horizontal changes and say, hey, back and then over, and then we can figure out the overall to get to the final destination. And then we could talk about the vertical changes. Like, oh, it went up, then it went up some more, then it went up some more. And then we could figure out by adding all of those, the vertical change. Why is it maybe nicer to break each of these little vectors down into their components? Why might it be easier to break each of these little vectors down into their components? Because at the end, what kind of triangle do you have? Ha-ha, a right triangle instead of all these weird little obliquey ones that are supposed to be like with geometry and parallel lines and alternate interior angles and angle additions and subtractions and segment this, that's, and the others. But it's a mess. Signs would have to be used multiple times to go this route as opposed to breaking them down into their components and then just putting them all together. So check it, components. Has anybody figured out what the word means? Taking a vector and figuring out how the horizontal and vertical, can be stated to show the overall effect. Basically making a vector into a net vector or an overall vector and saying, hey, he could have come from this horizontal piece and this vertical piece. Basically taking a vector and saying, hey, he could have come from this horizontal piece and this vertical piece. What's really going on is this vector from beginning to end, from tail to head. But we could break this vector down into basically forming a right triangle and saying, oh, hey, if you go over and down, it's the same amount. Not that if you were actually doing this journey, you would want to go over and down. If this was like that ship example, you wouldn't want to. Shortest distance between 2 points, just go there. But as far as putting together like multiple situations and trying to find the overall effect, it's a lot easier to break it down. And so components, one way of thinking about it could be an A measurement and a B measurement. We're not actually going to make them vectors right now. I'm just going to talk about length. So let's take off the little arrows, even though those are important. That's where the I's and J's come in a little bit later. Literally how far over and how far up or down. So vector RS could actually be rewritten as the horizontal change and the vertical change, but not in parentheses, not in brackets, but in, we're going to call it side carets. Not in parentheses, not in brackets, but we're going to call them side carets. When you see the side carets, that's going to be denoting a vector with its horizontal distance, vertical distance. The vector itself is the hypotenuse. The vector itself is the hypotenuse. And yesterday, didn't we talk about how a vector starts from an initial and goes to a terminal, right? A vector starts from an initial and goes to a terminal. So if that's the case, if we can say any vector can be broken down into like legs of a right triangle as far as the overall horizontal change, well then it should be easy to find the, what are these two lines denoting again? Magnitude, good. So the magnitude would just be the how muchness, and the how muchness would just be the Pythagorean theorem. So you can just say a squared plus b squared. Now, here's a little bit of a struggle. But how do we find A and how do we find B if we're given things like x2, y2, a point for S, and x1, y1, a point for R. We've talked about this, but it's been a while. How can we find A? Isn't it the horizontal difference? Couldn't we say that A would be the same thing as the two x's subtracting each other? Right? So it's as easy as saying, oh, hey, we can find that by just doing x2 minus x1. The terminal minus the initial. Ooh, that's important. The terminal minus the initial. The final minus the initial. That's the way like a physics class would say it. Where you are from where you were. Terminal minus initial. So the x2 minus the x1, or the point at the head minus the point at the tail, but that's just the horizontal. We also need the vertical, so what do you guys think? Yeah, there you go. Good application of the same procedure. y2 minus y1. Now it starts to get intense. The zero vector is the most basic vector because the zero vector just says, hey, I haven't gone anywhere. I haven't gone anywhere horizontally. I haven't gone anywhere vertically. That seems kind of silly, I know, but the zero vector. I haven't gone anywhere horizontally. I haven't gone anywhere vertically, which some of you guys are like, oh, it's the origin. Nope, not necessarily. It could be any point, because any point, if you're just at a point, question, has it gone anywhere horizontally? Has it gone anywhere vertically? He's a zero vector. What about that point? Zero vector. What about this point by itself? Zero vector. What about this point? Zero vector. Any point by itself, anywhere in space, remember, vectors are equal if they have the exact same magnitude and direction. Any point is going to have a zero vector, which is kind of weird. A unit vector, unit. Where have we seen unit this year? What's so special about the unit circle, about its size? What's 1? The radius is 1. So what do you guys think about the unit vector? What's its magnitude going to be? 1. AKA, a squared plus b squared has to equal 1, right? Okay. Joop, 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 joop. Let's keep going. So from all of this stuff, looking at or thinking about your next section of homework, which gives you pictures, first of all, and gives you points, second of all, labeling them initial and terminal. What do you guys think we're going to do if it says find the component form and magnitude of the vector v? Pause, time out, write the problem. And as you write the problem, pause. Problem, what are you going to do when you get to this little v right here? Put a line on top of it. Don't you dare try to make it bold or just ignore it. So whenever I see in notes something like this, I'm going to try to remind you by putting a little arrow. I'm going to try to remind you by putting a little arrow. You guys are staring at me. But do you see an initial side, even though they didn't label it? Or initial point, I should say. Who's the initial? 2, 2, good. Who's the terminal? The other one, right? How do you know that, my ones that answered it? Explain. Where the arrow points, the beginning is the initial, the ending is the terminal. Components, say, break it down. We can plug it into the formula real easy, hopefully. V equals, who's your x2? -1. x2. The terminal or the final x minus the initial x. Who's your final y? Just like slope, we're going to have to go the same direction. Does that make sense? But also make sure you're doing terminal minus initial. We can do the math really fast, hopefully, as long as you start to get the hang of this little, like, just terminal minus initial, because you're going to end up with -3, 2. But what does that mean in context of the picture? What's negative 3? Nope. Kind of. What's negative 3 specifically? What's negative 3? Huh? It? Oh, A. I've been saying, he's totally right, sorry. A. What's he mean? Wait, Wyatt. Good. How left it went? Left. Now, hold on. Technically, the negative is what puts it that way, right? So you could say it went to the left. True? So what's the 2 mean? How up it went. So it went positive 2 and negative 3. So kind of you could think of, even though the distance would be 2, the distance would be 3. It went up 2 and left 3. Remember, with vectors, there's this direction-y thing. That's also important. It's not just a random triangle being like, whatever, size. And we're used to that with unit circle, because unit circle, we had to think about the left and the right and the up and the down and the signs. Same thing with vectors. Because if you don't think about the signs, you could end up over here. That'd be bad. Right? So how should it make sense that the formula for the magnitude of the vector technically just says take these 2 numbers, square them, and square root them? Why should that make sense now that you see the picture? The formula says take him, square him, plus square root. Why? Why does it make sense? The magnitude will be the same thing as the what part of the right triangle? Hypotenuse. And what are these 2 guys? Got it. It's just Pythag. So therefore, what's your magnitude? You guys who've already done it. Is it 13 again? Man, we've had a lot of 13s. Sorry. Or root 13s. Are there formulas to plug and chug? Yes. But is there a picture, a situation, a scenario behind it? Yeah. Yeah. Some way, shape, or form, yeah. Let me take all this work and put it off to the side. With vectors, I want this to illustrate something really quickly for you. With vectors, there are going to be formulas that you could just plug and chug. And sometimes that's enough to memorize the formula and to plug in. But there are also going to be situation scenarios, especially in word problems, that technically give this or are modeled by this. There's this meaning behind the scenes. There's a situation, a scenario that could be put to the formulas that you guys are studying, memorizing, etc. So some of your brains are just going to need to memorize formulas like this page. It just is what it is. I'm going to grab out a highlighter. I'm going to highlight every single important one. Some of your brains are going to need to highlight and memorize formulas like the component form, formulas like the magnitude. Don't worry about these 2 for right now. They're not really memorizing ones. Some of your brains are going to need to strictly memorize and plug and chug, but just a few of you, if you can tie the formulas to the situation, the scenario, the picture, it will probably be somewhat eventually common sense, but not to all. Vector operations. Ooh, hey, did you guys see the next part of homework? What am I trying to do? Illustrate to you that my notes almost always go in order of the types of problems in the homework on purpose. On purpose. Sometimes I mix up the order and I let you guys know that every now and then. But usually, let me bring this down a little bit. Usually, I follow the order of the homework. Why? Because I want you to be able to split the homework up and do it little by little. Vector operations, the basics. They're so easy, you'll love them. At least the math. Because the basics say, wait, pause, get down the information, but every time you see a bold, what should you do? You don't write in bold, I don't write in bold, put the little vector arrows above it. You don't write in bold, I don't write in bold. Scalar. Sounds like a snazzy term, right? Scalar. Bless you. Guess what it means? You're just multiplying by a constant. Could be multiplying by 2, could be multiplying by 3, could be multiplying by 5 or 10. Scalar. You're multiplying by a constant. Scalar. You're multiplying by a constant. Anybody just want to take a guess as to what you think you do to the components? So for instance, we're thinking. Let me give you an example. What if this one was, couldn't this vector down here have something like negative 2, 2? Could that make sense? Left 2, up 2? Sure. So what do you think is going to happen if all of a sudden we have something like 3v? Would that make sense? Your vector is going to be tripled. So guess what the formula is going to be? A times v1 times a times v2. A times v1 times, or comma, a times v2. So if this was negative 2, 2, and I needed to triple the vector, which could be something like tripling the force, doubling the force. Uh-oh, Aiden's group, gotta help him out. Tripling the force. Tripling the vector. Or maybe you're going to go 3 times as fast, or 3 times as long. Instead of going negative 2 and positive 2, you're going to go 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. So whereas this one down here would have been little vector v, tripling it is as easy as, well, kind of, 2, 4, 6. How about that? Tripling it is as easy as tripling the horizontal and tripling the vertical. Nice. So we could do 3v1 and 3v2, which is what we did. Okay, vector addition. Oh man, that one was rough mathematically speaking. Nah, it was fine. But if you don't believe me, couldn't we figure out the magnitude really quickly of vector v? And figure out the magnitude of 3v? What would be the magnitude of the first vector? Square root of negative 2 squared plus 2 squared, right? Pythagorean theorem. So wouldn't that be 4 plus 4, which would be the square root of 8, which is 2 root 2? You guys agree? What would be the magnitude of 36 plus 36? 72. Does 8? Ooh, 9 goes into 72 8 times. So 3 root 8. Wait a minute, what's 8? 6 root 2. Hey, is it triple? Okay. But the math was easier than having to figure out the hypotenuses and then the magnitudes and then trying to triple it. We could have done that and then tripled it and then gone backwards to its components, but isn't it a lot easier just to find the components and say times 3 times 3? What do you guys think this one's going to be if you're just supposed to be adding? Really? Is it that easy? Which is why we love components. Well, components specifically, especially with vectors. because it all comes back to this picture. If we were trying to add vector u plus v plus w, it would be this resultant, this net that I talked about yesterday. To add vector u plus v plus w, if we didn't think about breaking down each and every one into components, we would have to deal with this geometry picture of how do I take this and all their little baby angles, which I would have this awkward angle for u. I would have this awkward angle for v. And then I would have this awkward angle for w. Who wants to deal with the geometry diagram to try to figure out what length is? But if we figure out an x and an x and an x, we can add them all to get the x. And if we figure out the y and the y and the y, we can add them all to get the y. This is super practical, super applicable. And all you have to do is say, get the components and just add. Get the components and just add. And then life is easier. So what if I was to give you something like this? Let me just make it a little bit easier. There we go. And we called the purple guy vector v over here, right? So let's have our vector v being negative 2, 2. And let's have our vector w, he'll be the other guy, being negative 1. Could that work? For purple, negative 2, 2. And for w, negative 1, negative 1. That could work, right? Just addition. What happens when you put those two together? It's as easy as negative 3. The math's easy if you have components. When is it not easy? Wait a minute, negative 3, 1. If that's 2, negative 3. Who sees that obviously working? Wait, that's negative 3, negative 1. Okay, well, you shouldn't see that working. Lo siento. 1, 2, positive 1. Is that super obvious why those two add to be this one? But wait, the roller coaster yesterday, I thought you flowed through one and was the other. I don't get it. Are they flowing through each other right now? How do you make them flow through each other? Exactly, which is why this is so much easier, right? But that's technically how it works. You'd have to actually like transfer, rotate, move this angle, and as you move this angle, you have to think about all this geometry where you might know this angle, but if you move it, all of a sudden you're like, well, what's that angle? Oh, stink, I have to, well, think about, and then the rotation, and then, parallel lines, and then you'd have to think about all kinds of geometry stuff, which and you would have probably done it in geometry. And we'll do one example like that at some point, the hard way, the geometry way. But wasn't the math so stinking easy? Without even thinking of the picture, it was like, let me just break him down. Let me break him down and let me add. Oh, sweet, done. Over together in your force diagram or your vector diagram, and you're like, oh, it works. In components, the math is easy. Once you have the components. I want you guys to draw me a vector u. I want you, oh, sorry, you can't even see it. I want you to draw me a vector u. I want you to draw me a vector v. Oh, what should you be putting on top of the u? What should you be putting on top of the vector v? When you're writing your homework, the directions, the problems, you better be putting those arrows on top. Draw me vector u and draw me vector v. Using those components, get me a picture. We're not just going to do the math. Because look, we also need to sketch each result. We're not just going to do the math. In some physics classes, an AP physics class we used to have here on campus, there was a day that all the physics kids were bringing their rulers and their protractors because they were making vector diagrams the long way. It's awesome. There were tons of forces at work too. There is a reason. I'm not just trying to make your life awful. What quadrant is vector u? Well, how do you get to vector u? Where'd you guys start from? I'm guessing everyone started from, but you didn't have to, but you could. Starting from the, probably. But you would start there. But in physics, you could technically start from anywhere, but that's okay. How right or left did you go? And then how up or down did you go? Now hold on. Which direction did you go? Why did I go to the right? And then I'm going to go up or down? Good. So there's vector u, true? Okay, there's our u. Oh, arrow got lost. Where's vector v? How do I get there? Oh, we could go up 3. I think I'd rather go right 1 first. Is that okay? And then up 1, 2. We good? Are they flowing together yet? Nope. Okay, there's our vector v, there's our vector v. We have up 1, over 1, up 3, and we have over 2, up 1. How do we add them? Oh, that's okay. Add the components. So what's vector u plus vector v? What do you guys got? As easy as that. Didn't even have to look at the picture. How about u minus v? One, -2. Why? You can't just go the way that your brain would rather. If it's u minus v, v is being taken away from u, aka v's components are opposite, -1, -3, and then adding. It's 2 minus 1 and 1 minus 3. You can't go the other way around because is subtraction commutative? No, I can't go v minus u and have it be the same. Careful, careful. How about letter C? What? Have you guys figured out how to put this all together? What would 2u end up being? What would 3v end up being? Yeah, 3, none. Then what were you supposed to do? Put them together. What's 4 minus 3? What's 2 minus 9? But are there scenarios behind the math giving some meaning to what we actually just did? Yes. Ah! Okay, I give up. Yes. You're all right, you're all right. What do I have in all 3 of these so far? Just UV. One letter A said U plus V. Guys, shouldn't I be able to sketch 3, 4 pretty quickly? 1, 2, 3, 4. But how does that make sense? Oh no. Coming over to the screen. Every now and then my computer doesn't work with me. What happens if I flowed through one to get to the other? Okay, so my mind's a little bit off. But does it work? Yeah, flow through and you get your 3, 4. What does this mean, U minus V? 1, -2. I mean, I could graph it, right? Go over 1, down 2, no big deal. There's the 1, and then go down the equivalent of 2-ish, here-ish. I'm very much approximating. How do they flow together that way? Who's your U? Blue, right? U minus. How do I minus V? What's minus V actually mean? Going the opposite direction. Oh, does that make sense? If you flip the signs of a vector, won't the tail or the head be going, I should say, the other way? Oh. So multiplying a vector by a negative is actually flipping the direction. How about 2u minus 3v? We have our 1, -7 as our final result, right? 1, -7, I could go ahead and go over my 1. Uh-oh. Then I have to go down 3 more, and then 7. Okay. I'm not sure how close I'm going to be on this, but let's try. What's going to happen to my u, guys, if it's 2u? It's going to be doubled, right? Twice as long. What's going to happen to my v if it's tripled? 3 times as long? But hold on, what else happened to the v besides tripling? The direction also just flipped, right? Does it make, oh, I was close, sense? Yes. All right, you should be able to at least get up to number 30, if not a little bit beyond. And tomorrow, we have to put all this stuff behind to get to situation word problems. But is the math hard with components? Nah. See you later, bye. See you later, bye. Okay. So I have Adam, I have Kim, and I have a group of 4. Sorry, Jason.